I've received some questions about number 20, both in my office hours and by email. So let's think about that. You guys have different numbers, I believe. So the problem is that consumers know that some fraction X of all new cars produced and sold in the market are defective. The defective ones cannot be identified except by those who own them. Cars do not depreciate with use. Consumers are risk neutral and value non-defective cars at $20,000 each. So new cars sell for $16,000 and used cars for $12,000. So the key to this problem is that given the situation, the price of a used car is going to be the value of a defective car, because remember that only defective cars are going to be sold in this situation. We might naively think that the price in the used market would be a weighted average of the value of a non-defective car and the value of a defective car. But at that price, only people with defective cars would be interested in selling. The people with non-defective cars wouldn't be able to sell for the value of the car, so they'd keep the car, is the logic there. And so once we know this becomes a much easier problem. It's always easy once you see the gist of the problem. So we know that some fraction X of cars are defective, and we now, with this realization about Akerlof's lemon law, we know that the value of a defective car is $12,000. So the value of a new car is going to be a weighted average between the value of a defective car and the value of a non-defective car. And if X are defective, that means 1 minus X are not defective. There's only two possible states of a car in this problem. Obviously, in the real world, it's a little more complicated. Anyway, the new car price is that expected value. So now we have one equation, one unknown, and we can just solve this. So let's multiply out the 20,000 times 1 minus X and then isolate X. So 12,000 X plus 20,000 minus 20,000 times X is equal to 16,000. Now let's move things around. Notice that if I combine terms with X in them, I get negative 8,000 X, negative 20,000 plus positive 12,000. Then I'm going to move that 20,000 over to the other side. I'm going to subtract 20,000 from both sides. So I get negative 4,000 on the right-hand side. 16,000 minus 20,000 is negative 4,000. And then I can divide through by negative 8,000. To get X is equal to 4/8, which is equal to 1/2, which is equal to 0.50. No student has complained that putting in 0.5 has gotten a wrong answer, but when they ask for an answer to 2 digits, I would, just to be on the safe side, enter 0.50 just to be, just to get it at 2 digits. I've seen that problem before and connect. It's dumb, but it's once you realize it's happening, it's easy to accommodate that. All right, that's what there is to that one.